Have you ever wondered how to make trillions of atoms masquerade as one in a single quantum mechanical state? In this video, I will bring you to a Class 100 cleanroom at the Chalmers University of Technology, where I will show you how we fabricate superconducting devices that enable us to research interactions between light and matter and serve as building blocks for quantum computers. Hi, my name is Janka, and during my journey as a PhD student at the Chalmers University and the Wallenberg Center for Quantum Technology, I have done research focusing on fabrication and development of quantum devices, including superconducting qubits. And here I will show you how I would go about making such qubits. Unfortunately, I won't be able to get into the details of how quantum computers or superconducting qubits work here, because that would really warrant a separate video. But in an extremely condensed nutshell, quantum computing is an emerging technology where we encode information in quantum mechanical states. And we aim to leverage the possibility of quantum superposition and entanglement of states to achieve up to an exponential speedup in solving certain classes of computationally hard problems over classical computers. There are different promising quantum computing technologies being researched around the world, but in my PhD I focused on the superconducting quantum computing using transmon qubits, so that's what we're going to make here. But before we jump straight into the fabrication, let me introduce the star of the show, the device.
We will start off with a wafer of silicon, which is a very standard substrate material not only in the semiconductor industry, but also in the world of superconducting devices. And on top of this silicon, we are going to build the qubits and their supporting structures out of a superconducting metal, which in our case will be aluminium. A very basic qubit device may look something like this under a microscope. Starting from the top, we have a piece of an input-output transmission line through which we can send signals to the qubit, let them interact, and then measure the results on the other end. To this transmission line is coupled a rather simple resonator, which can be approximated as an LC oscillator. And this resonator helps us control the qubit and read out the quantum state that the qubit is in. And then the actual qubit is this guy over here. A transmon qubit consists of a large capacitor, which in our case is this big cross, and then another very important building block would be this element over here, which is so tiny I needed to use an electron microscope to zoom in on it properly, but what it is a so-called Josephson junction, also known as a JJ. A JJ is a relatively niche circuit element where two superconducting electrodes are separated by a thin, non-superconducting barrier. So remember, all the circuitry we are looking at is going to be superconducting when we use it. But if we construct a small barrier here where the superconducting path is interrupted by, for example, a thin layer of insulator, that will give rise to a nonlinear inductance in the circuit. And very long story, extremely short, this nonlinear inductance makes it so that the separation between the different energy levels of the qubit that we can interact with is different from one level to another. So if we assign labels to these energy levels, like for example, I don't know, 0 and 1, we can choose to interact with these levels and these levels only at their given energy frequencies. In the resonator, which does not have this nonlinear inductance, all the energy levels are spaced equally. So we can't address specific levels this way, and therefore a resonator would make a really lousy qubit. It is, however, extremely useful as a supporting structure in quantum processors. So that is what a single qubit unit looks like. Now coming up to wafer level, this is the design we are going to work with. It contains many chips that can be all used separately, and then each chip contains multiple qubits. In the pattern, everything that's in white is the superconducting aluminium. And then what's in green is where we create gaps in the metal, revealing the underlying silicon, and then the resulting structures left behind in the aluminium can act like our various circuit elements. Looking at the pattern of a single chip, we have the input-output transmission line, which has these pads on each end where we can bond wires that bring signals in and out of the device. We will also have the Swiss cheese pattern happening all over the chip. Those are magnetic flux traps and are here to give the qubit extra on-chip shielding. So those are the basic features of the device. There is more stuff on the wafer design like alignment marks for different patterning steps or special process verification structures. But the key ingredients of a superconducting transmon qubit device is basically what we just went through. Now the plan of battle is, we take a substrate, we deposit a superconductor film on top, we pattern the film with the resonators, capacitors and flux traps, and then we make the Josephson junction separately because they're a bit more complicated.
The lab we're going to fabricate the qubits in is a so-called cleanroom laboratory. This one here at Chalmers is a part of the Myfab network of nanofabrication laboratories and provides us with a top-notch cleanroom infrastructure and very helpful and knowledgeable staff. A cleanroom is a special kind of lab where a lot of effort is put into minimizing the number of particles circulating in the air, as well as into controlling environmental conditions such as humidity, temperature, and pressure. The reason for that is that the dimensions of the devices that we make here are very, very small. so small that they are invisible to the naked eye at only a fraction of the width of the human hair. For something that small, it would be disastrous if, for example, a speck of dust fell in at the wrong time and got trapped inside. That could essentially break the entire device. So we go to great lengths to avoid that. The main lab area that we do most of our processing in is a class 100 cleanroom, which means that the maximum number of particles permitted per 1 cubic foot of air is 100 in the lab. To achieve that, the cleanroom is at all times ventilated from top to bottom with heavily filtered air, giving the lab a constant shower of very clean air. There are also very strict rules on what kind of items and materials we are allowed to bring into the lab. For example, even the paper we use to write notes on is a special kind that doesn't shed. It is also not permitted to wear cosmetics inside the cleanroom, and I will have to put on a special protective suit before entering. The biggest source of contamination in a cleanroom are actually the people working there. So a human at rest can generate well over 100,000 particles per minute, while a person walking quickly can generate above 10 million particles in that time. Therefore, when working inside a cleanroom, it's important to move in calm, collected movements and to wear protective clothing at all times. So suiting up, I have already started with a hairnet, over which will go a hood, coveralls, boot covers, and also gloves and goggles. If you look closely, there are these conductive wires woven into the fabric of the suit, so that when I'm wearing this thing, it basically forms my own personal Faraday cage. The reason is that a great way to damage a sensitive nanoscale device is through electrostatic discharge, where if your sample gets zapped from you, you could essentially fry the entire thing, which we generally try to avoid, so the Faraday cage is there to help prevent that. One thing worth noting is that all of these garments are not really there to protect me from anything inside the cleanroom, with the exception of the goggles. They are there to protect the cleanroom and my sample from me and the particles I shed. So if I want to do something potentially hazardous in the cleanroom, like for example handling chemicals, I will have to put additional layers of protection on top of all this. The substrate that will form the base on top of which we will build our qubits is silicon. This silicon wafer is about 0.5 millimeter thick and 4 inches in diameter, which is quite standard for research and development purposes. In an industrial application, the wafer size would typically be a bit larger. The first step in our process is to clean the surface of the silicon wafer before we deposit the superconductor on top of it. The thing is, a silicon wafer, if left for long enough in ambient air, will inevitably grow a thin layer of silicon oxide on top, which we don't appreciate in our devices, so I'm going to remove it by drowning the wafer in hydrofluoric acid, also known as HF. HF will remove the silicon oxide, and with it hopefully also lift off any kind of junk that may have accumulated on the wafer surface before it got to our loving care. But it will not damage the underlying silicon. Instead, it will leave the silicon passivated with a single layer of hydrogen that, as an added bonus, will repel water and temporarily prevent the silicon from reoxidizing. Because HF is quite a nasty piece of work, I'm going to have to take some extra precautions. I may have mentioned before that what I'm wearing now is not really here to protect me from anything inside the cleanroom, but is rather to protect the cleanroom from me. If I need extra protection for example, acid work, I'm going to need to put some extra layers, like for example, a face shield, an apron, and a pair of extra thick chemically resistant gloves. So this is the acid gear in all its glory. The chemical benches also have some safety features themselves. For example, they are being constantly ventilated to remove chemical fumes, which is incidentally why it's allowed in here. But the ventilation is so good that even if I was working with something as stinky as acetone, so glorified nail polish remover, I wouldn't be able to smell it from where I stand. That's how good it is. HF, however, because it's so nasty, I'm not going to actually handle it myself. It's going to be in a permanent bath where I'm going to submerge the wafer and then rinse it off in water afterwards. For my own safety though, I'm going to do that off camera, but I'm going to show you what that does to the surface of the wafer afterwards. Here we have a side-by-side comparison of two silicon wafers, one that I did not treat with HF and one that did receive the HF treatment. You can see how the HF-treated wafer repels the water I spray on. The water forms small droplets to minimize its contact area with the now hydrophobic surface of the wafer, and the droplets fly off as soon as I spray them with a stream of nitrogen gas. On the other hand, the native oxide of the untreated wafer is hydrophilic, and the water forms a giant blob that is quite a challenge to spray off. There are many different ways of depositing a metallic film onto a substrate. In this step, we'll use a technique called sputtering, where we'll place our substrate into a vacuum chamber facing a source of the material we want to deposit, which in this case will be aluminium. The chamber is then flooded by a heavy but non-reactive gas, and the plasma of this gas is then ignited by applying a voltage across the chamber. The plasma ions bombard the source, knocking out atoms from it, which then land on the substrate, forming a thin metallic film. So now we are at the sputtering tool where we're going to deposit the film. And this is the deposition chamber where we're going to do it, which is currently sitting at a very good vacuum where the pressure is somewhere below 10 to the minus 8 millibar. And the reason for that is we want to avoid contamination of our films during deposition. To avoid destroying this vacuum with atmosphere every time somebody wants to load a sample, we have a separate load lock here, separated from the main chamber with this big sturdy gate valve. And what I'm going to do is I'm going to take the sample, put it in the load lock, pump the load lock down, and only when I'm happy with the pressure, I'm going to open the valve and transfer the sample into the deposition chamber. Now that the air has been sufficiently pumped out from the load lock and the vacuum is good enough in there, it is time to open the gate valve separating the load lock from the main deposition chamber and to transfer the wafer inside. Looking inside the deposition chamber, we have the silicon wafer at the bottom of the screen and the source of the aluminium above it. The argon plasma is now ignited, but there is a shutter between the substrate and the source which shields the wafer while the plasma stabilizes and the potentially oxidized or otherwise contaminated top layer of the source is removed. When the shutter is open, the argon plasma, accelerated by a voltage across the source and the substrate, knocks out aluminium atoms from the source, which then land on the wafer, forming a thin metal film. So this is what a sputtered aluminium film looks like on a wafer. The film is so thin that we wouldn't be able to really see it looking at the wafer from the side, but looking at the front of the wafer, we can see how the previously dark gray color of the bare silicon surface has been replaced by the mirror-like finish of the aluminium film. So we started off our fabrication process with a bare silicon wafer, on top of which we deposited a layer of aluminium. Now we would like to pattern this aluminium with our various circuit elements, such as qubit capacitors, readout resonators, and input-output transmission lines. Since many of the elements we want to pattern are so small they're invisible to the naked eye, we can't exactly have a go at it with a hammer and a chisel. Instead, we will resort to a process called photolithography. The way we're going to do this is we're going to first deposit a layer of photoresist on top of our aluminium film. A photoresist is a polymer that's sensitive to certain wavelengths of light. And what we can do is we can take a layer of this photoresist and selectively expose certain areas of it, for example, where we would like to have the gaps of our qubit capacitors, to light of this wavelength. This will chemically change the exposed areas of the resist, which in our case will make them soluble in a liquid we call photodeveloper. And if we then take this selectively exposed resist and submerge it in a beaker of this developer, the exposed areas will be dissolved, while the unexposed areas of the resist will remain behind on the wafer. And this way we can create a pattern in the photoresist layer on top of our still continuous aluminium. When we then want to transfer the pattern defined in the photoresist layer into the actual metal underneath, we will simply submerge the wafer into an acid that reacts with aluminium, removing it from the surface of the wafer in a process called wet etching. The areas of aluminium that are covered by the remaining resist will be protected from this acid attack and will also remain on the wafer. The exposed pattern will be etched away. To just quickly summarize all of this before we move on. To pattern our aluminium with the desired circuit elements, we will first cover the wafer with a photosensitive resist. Then we will expose our pattern into the resist with a laser beam. We'll develop the exposed pattern, after which we'll get a pattern resist layer on top of a still continuous layer of metal. And finally, we will etch this pattern into the metal using a corrosive acid. After this, we will no longer need the resist layer and can simply dissolve it in, for example, acetone. So that's the version of the photolithography process we will use in this patterning step. Now let's head out to the clean room and get started with the resist deposition. Now we're at the station where we will coat our wafer with the photoresist. You may have noticed that this part of the clean room is a bit yellow. That is because the wavelengths of light that the resist is sensitive to are filtered out in this section, leaving behind this very flattering yellow glow. We'll deposit the resist on the wafer using the spin coating technique. I have placed the wafer on a spin chuck where it's held in place by vacuum. The next step is to pour some of the resist, which is liquid for the moment, in the center of the wafer. The spinner will then spin the wafer crazy fast to spread the liquid into a uniform thin layer coating the surface. My apologies for the lid of the spinner blocking your view, but it's there for safety, so that in the unlikely event that the vacuum holding the wafer in place breaks halfway through the spinning, the wafer doesn't fly in my face. After spinning, we should have about half a micrometer of resist covering the wafer, with the excess liquid having been flung off the surface towards the edges of the spinner. I will shortly bake the resist on a hot plate to evaporate any residual solvent, solidifying the liquid into a thin layer into which we can expose our pattern.
This beautiful machine is a laser writer, and I have just uploaded my pattern into its computer, and what it's going to do now is it's going to scan over my wafer, drawing this pattern into the resist with a laser beam. And this then makes this pattern exposed into the resist soluble in a developer afterwards.
Now the design has been written into the resist, but we can't actually see it until we develop the pattern in the developer. If you look closely towards the outer edges of the wafer, you should start seeing a color change as the resist dissolves there, and soon we should also start seeing traces of our qubit chips appearing in the center of the wafer. Once we are done with the development, we can stop the chemical reaction in a beaker of water and then dry the wafer under a stream of nitrogen gas. Now we can see a faint pattern on the wafer, but remember, the pattern is not actually present in the metal yet. It's only written into the resist layer covering the metal, and the aluminum underneath is still continuous. To transfer the pattern into the metal, we are going to submerge the wafer into an acid which reacts with aluminum. The areas of the metal protected by the resist will be unaffected and will remain on the wafer, but whatever aluminum is exposed to the solution will be removed. Now we can see some black areas appearing on the wafer, starting from the edges. That is the underlying silicon substrate peeking through, in the spots where there was a gap in the pattern resist and the unprotected aluminum was allowed to have direct contact with the etchant solution. After the full pattern has been etched into the metallic layer, we can stop the chemical reaction in a beaker of water. And more water. The wafer is currently taking a swim in what we call the quick dump rinse bath, which goes through several cycles of spraying the wafer and filling the bath with pure deionized water and then dumping the contents. This ensures that the acid is properly rinsed off the wafer surface, which is important not only for the safety of the people handling the wafer, but also so that there are no acid residues that can further corrode the metal after we're done with the etching. Incidentally, I have also used the quick dump rinse after the HF treatment back at the very start of this fabrication process, but there the copious rinsing was mostly there for human safety than that of the wafer. So now you can see the pattern etched in the aluminum. We can't actually see the qubits because they're too small to see. But if we took a look under a microscope, we would see that we have almost everything there apart from the Josephson junctions, which we will have to do separately. The metal looks a bit yellow, but that's because we still have the resist covering it. And since we don't need it anymore, I am going to remove it in some solvent and I will meet you at the next step. The next step is to add the Josephson junctions, which will be the nonlinear inductance elements that will turn our harmonic oscillator into an actual qubit. The junction type we're going to make is the SIS, or the superconductor insulator superconductor junction. The superconductor will be once again aluminium, same as the rest of the circuit, and the layer of insulator that is sandwiched between the two superconducting electrodes is going to be aluminum oxide. The way we grow these junctions is quite straightforward. We will first deposit a layer of aluminium to form the bottom electrode, then we will flood the deposition chamber with pure oxygen to grow a layer of aluminum oxide on top of this bottom electrode, and finally we will deposit another layer of aluminium on top of all this to form the second electrode. How we actually define the circuit on the wafer and how we make sure everything is where it's supposed to be and is also connected the way it's supposed to be gets a little more complicated. First of all, the junction electrodes are super narrow. They're so narrow that we can no longer rely on our laser writer to expose them because the pattern would be smaller than the wavelengths of its photons. Instead, we will resort to electron beam lithography because we can get appropriately narrow wavelengths out of electrons much easier than out of photons. The actual patterning technique is in a sense the opposite of what we did before. Before we took the substrate, deposited a metal on top, then patterned a resist on top of the metal and transferred the pattern into it. What we're going to do now is we're going to first deposit a resist on top of the substrate where we want the junctions. We're going to pattern this resist and only then deposit a metal. Now we have some metal in direct contact with the substrate and some that is spaced by the resist. If we then dissolve the resist, then whatever metal was on top of it will be removed and only the metal in direct contact with the substrate will stay. So when we left the clean room the last time, we had just etched the big circuit into the metal, and I was going to get rid of the remaining photoresist. Now I'm going to spin coat the wafer with a fresh coat of resist, this time one that is sensitive to the short wavelengths of the electrons generated in our electron beam lithography system, and I will meet you at the e-beam tool.
So this magnificent beast is an electron beam lithography machine, and what it's going to do to our resist is the same thing as the laser writer did, except it's going to do it with a 100 kilovolt electron beam. So the mechanics are very different, but the principle is the same. We have a resist into which we're going to draw a pattern using the electron beam, which is going to make the pattern soluble in a developer solution.
First, I'm going to mount the wafer on one of these specialized loading cassettes. They are a delicate piece of engineering, very fragile, very expensive, because they are machined with extreme precision to enable me to finely adjust the rotation and tilt of the wafer. They also act as a very stable point of reference to the exact position of the wafer in the system, and also to the position of the alignment marks I made on the wafer in the previous patterning step, so that both patterns made in these two separate lithography processes can overlap and match as they should. Once the wafer is securely mounted onto the cassette, I can place it into the load lock of the e-beam system, which is then pumped down to a low pressure, and the cassette is transferred onto the writing stage of the system. Unlike with the laser writer, we will not be able to see directly what's happening inside while the pattern is being exposed, because it needs to happen in a shielded chamber. But we can monitor the effects of the electron beam firing on the screen, sort of like with an electron microscope. Once the pattern is exposed into the resist, we can develop it in a beaker of developer, same as we did in the previous lithography step. Because the JJ electrodes are so small, we will not see any changes on the wafer with the naked eye once we develop the pattern, but if we take a look at just one of the qubit chips, and then zoom in on this tiny area here by the qubit capacitor using a high magnification optical microscope, we can see the gap in the developed resist where we intend to deposit our junctions. In this microscope image, we can see the aluminium as the lighter areas reflecting the lovely cleanroom yellow. The dark areas are the underlying silicon, and then the whole thing is covered by resist, apart from the aforementioned situation here in the center, where the gap in the developed resist defines where we want to have the two electrodes that will form the Josephson junction at their intersection. We have also already defined the angular patches that will connect one of the electrodes to the qubit capacitor and the other electrode to the ground. Depositing the Josephson junctions will require us to get a bit clever, because 3 different depositions need to happen at 3 distinct places, but they need to happen one at a time. We need to first deposit the bottom electrode, then we need to grow the insulating oxide on top, then we need to deposit the second electrode, which will go over here, and only then we want to put the connecting patches on. The problem is that we already have all of these regions opened in the resist, so to be able to selectively deposit to only one of these regions at a time, we will use a trick called shadow evaporation. In this technique, we will deposit the metal from an angle as opposed to just straight from the top as we did before. And what that does is that if you have a cross pattern like this one here, if we deposit from the north direction at an angle of say 45 degrees, then the resist stack that is behind the west-eastern trench will block any metal from depositing along that direction, and only the north-south electrode will be deposited. If we then deposit the second electrode from the east, then the north-south trench will be protected, and only the west-east electrode will be deposited. Afterwards, we can repeat this exercise for the patches at their corresponding rotation. In this step, we will deposit the aluminium by evaporation instead of sputtering, which is slightly different. In sputtering, we dislodge the atoms from the material source by plasma ion bombardment. In evaporation, the metal source is heated up by, for example, an electron beam, so much so that the metal melts and evaporates, and the vapor of this metal then condenses on the substrate. This time, to also make the shadow evaporation work, we will tilt the substrate 45 degrees with regards to the source. We will also rotate the wafer in between the 3 consecutive depositions to guide the evaporated aluminium into the current resist trench of choice. Unfortunately, evaporation is not as spectacular to witness as sputtering, so I don't have much to show you here. So I'll skip ahead to when I have completed all 3 consecutive depositions and then ready to unload the wafer. Now the entire wafer is covered in aluminium and the pattern is hidden underneath. You can sort of see it when you move the wafer around. So now I'm going to immerse the wafer in a solution that will dissolve the resist and thus lift off the metal sitting on top of it. Okay, now you can see that the metal surface got a bit bubbly. That means that the resist remover has had enough time to seep through the openings in the pattern resist, so we can probably start the lift off. To help that, I'm going to introduce some liquid flow with my trusty pipette, and hopefully the metal will get a hint and leave. Sadly, the junctions are way too small to see just like this, and to admire our handiwork, we need to go take an image using an electron microscope. Once we confirm that the JJs are okay, we're basically done. Now we have fabricated all the crucial parts of the qubits, so it's time to dice the wafer up into individual chips that we can use. We'll do that using this menacing fellow over here called the dicing saw. It has a very thin and sharp blade, and it's going to spin that blade at 25,000 rotations per minute to make very precise cuts, dicing our wafer into small chips. I've gone ahead and covered the wafer with photoresist again, not because we're going to do any lithography anymore, but to protect my device from all the debris that will start flying once this guy gets to work. You see that there is quite a strong stream of water flowing constantly against the blade, and that's because things get pretty heated during dicing, so we need to use cooling water to avoid overheating as well as to remove debris. This strong water flow is why it is very important to attach your wafer properly to the mounting tape, so as not to suffer great material and emotional losses. So now we have our wafer nicely diced into individual chips. I am going to remove the protective resist and clean the chips up, and then they will be essentially ready from the fabrication point of view. Afterwards, the chips would typically be mounted on a connectorized sample box and then placed inside a dilution refrigerator where they can be cooled down to near absolute zero to harness their true superconducting properties. But that's a story for another day.
So there you have it. This is how we make a superconducting qubit. I left out some parts of the procedure that would make this video a bit too long, like for example how we check the quality of patterning after each step, how we calibrate fabrication processes or verify the electrical properties of the structures we make. And I also left out the countless intermediate surface cleaning procedures, but in a nutshell, this is what would typically go into fabricating superconducting transform qubit chips in the quantum technology lab at Chalmers. If you're interested in more details and further reading, the theses written by the lab members are publicly available online, and I will put a link in the description. If you made it this far, I hope you enjoyed and that you learned something, and thank you very much for watching.